So today I'm really going to mess with you, and I'm going to tell you that there's a whole nother number system that we have to learn about, and it's the complex number system. So it's commonly referred to as having imaginary numbers or imaginary solutions, and then usually the first thing an Algebra 2 kid would say is like, it's imaginary, so why do I have to consider it? Well, they use that as a way to determine that we're working in the complex number system. So what we have to think about is, up until today, when I asked you to take the square root of a -4, if you type that in your calculator and you were in real number system mode, it would give you an error message. It would say it's a non-real solution. Well, that's if we're assuming we're only considering the real number system. So, long time ago, someone decided, like, hey, the entire number system that we currently work with is created by us, by man. So what if we created an alternative number system that allowed us to do this problem? Because if you can start taking the square roots of negative numbers, that opens up an entire branch of mathematics, and you should be very thankful for, I believe it's Mr. René Descartes, who is attributed to coming up with the complex number system, or at least utilizing it, because this is what allows all of your electronics to work. So, yay. Here's the basis of the imaginary number system. Since I can't solve x squared equals -1 in the real number system, what if we consider the number I to be the square root of -1? And then if you think about that, if I is the square root of -1, and then I use my algebra skills to square both sides, that means that anytime I run into the number I squared, I could replace that with square and square root would cancel, a -1. So those are the two big things today, that I is the square root of -1, and that I squared is -1. This gets a little more complex, no pun intended, or actually pun intended, when you move on to higher math. But these are the basics for us in Algebra 2. So if I look at the square root of -4, now that I know that there is such a thing as a complex number system, what I can do is I can break that up into the square root of 4 times the square root of -1. And I already know the square root of 4 is a 2, but the square root of -1 we just learned is the number I. So this was going to reduce to the answer of 2I. So this is going to be a good time. Alright, let's talk about the powers of I. So I to the first power, just regular old I, we just found out was the square root of -1. Well, if I was to square this number, that would give me a -1. But what if I had I to the third power? Well, I would like to think of I to the third power as I to the first power times an I to the second power, since those are the two things I know. So if I remember that I squared, I should have done that in green, sorry. If I squared is -1, this is just a -1 times an I, which is -I. And you know what? I need to modify this a little bit. Square root of -1, let's just call that I. Square root of -1 is gross. Alright, I to the fourth power. Can we rewrite that as I squared times another I squared? Well, I just found out that I squared was -1, so this is really a -1 times a -1. That's just a positive 1. I to the fifth power. We can break it up a few ways, but what if I broke it up into the I to the fourth power times I to the first power? Well, we just learned that I to the fourth power is a 1 times I would be I. Should change my color, my bad, red. I to the sixth power, again, we could break it up a few different ways, but what if I broke it up into the, I don't know, I to the fifth power times I to the first power? So we just learned that I to the fifth power is I, and then I is I, and if we multiply I times I, we get I squared, but wasn't I squared -1? Uh-oh, in the words of my small children, there's a pattern. So I, -1, you guessed it guys, the next one in the pattern is -I, and then the final one in the pattern is +1. So, whoops, turns out that if you have what we call the powers of I, they repeat in a cycle of 4, and this is the pattern. Oh gosh, my cursor's not working. Get out of there. It repeats in a pattern of 4. It goes I, -1, -I, and 1. And it just keeps repeating over and over and over again. So once in a while you get a crazy question like I to the 300th power. Well, I'm not going to sit here writing out 300 I powers until I get to the final answer of I to the 300th power. What we're going to do is we're going to figure out like where in the pattern this number would fall. Well, the first thing I'm going to do is I'm going to divide this by 4. And it does divide evenly by 4. I believe it's 75. With no remainder, which means it would be at the beginning of the pattern because there's no remainder. Sorry, the end of the pattern because there's no remainder. So we're not going to get into like I to the various powers in our class, but when you move on to pre-calc, we're going to have you evaluate this, and then you're not going to be able to use a calculator to help you in any way other than like maybe with a little division. But if you end up with a power of I when you divide it by 4 and you figure out that there's no remainder, that means you're at the end of the pattern sequence. If there's a remainder of 1, you're at the beginning, remainder of 2, you're here, remainder of 3, you're here, remainder of 4, you're there. All right, so that was just a little prelude to pre-calc. I know a lot of our Algebra 2 students are going on to pre-calc, so look forward to that. You will learn all about it in pre-calc. Let's talk about simplifying radicals. This is going to be a big task for us in Algebra 2. The square root of negative 9. Up until today, I would say I can't do it, but now I can. 9 is a perfect square, but because of the negative 1, let's throw a negative 1 in another perfect square, and then remember that square root of 9 is 3, and square root of negative 1 is I. Notice there's no plus or minus because we're simplifying numbers. We're not solving anything. And here on number 2, we're going to break this down into, if this was just a 6, I wouldn't be able to break that down at all. So I'm just going to leave that as the square root of 6. But the thing I will be able to break down is the negative 1. Now this time, and it doesn't really matter, I'm going to choose to put the negative 1 first because that's the radical that's going to reduce. So this becomes an I, and then the square root of 6 is not going to break down. So this is how I'm going to leave my answer for Algebra 2. But if you go on to another class, you might see the negative 6 written first, and then with the I written off to the side. The reason I write the I first is because I have really sloppy handwriting, so sometimes the radical bar will kind of like go over the I, and that would be really incorrect. So you're going to see me always write it with the I in front of the radical if there's still a radical left. There was no radical here in number 1, that's why I didn't do it that way. So here for number 3, if this was just 8, I would be breaking down 8 into 4 times 2. But it's not just 8, it's going to be 4 and 2 and negative 1. So the order that I'm going to write this in, when they partially break down like this, I'm going to write the perfect square first, and then I'm going to write the negative 1 in the middle, and then I'm going to write the leftovers over here. And if you keep it in that order, it's a V, if you keep it in that order, it'll break down real nice for your simplification. So perfect square, negative 1, and leftovers. So the perfect square component of 8 is a 4. Negative 1 is negative 1. And then 4 times 2, 2 would be the leftover part. So now I'm going to simplify. And the square root of 4 is a 2. The square root of negative 1 is an I. And the square root of 2 does not break down. So this is the order that I would like to see them in. Perfect square, negative 1 if there is one, and then leftovers. And you could have used that for all these problems here, right? Perfect square, negative 1, there were no leftovers. There was no perfect square, negative 1, and then the leftovers. So using that same pattern here, 32 has a pretty big perfect square inside of it, so make sure you go big enough. It is 16 times 2. So I'm going to put the 16 in this front one, and the 2 in the leftovers part. Negative 1 right in the middle. So square root of 16 is a 4. Square root of negative 1 is an I. And then square root of 2 is square root of 2. So, I don't know, 3-4 years ago, I forget, I had a kid who was pretty clever, and they were trying to figure out a cute way to remember about the I, because it was a little confusing to them. They just learned about it in Algebra 2, and they said, oh, it's like, if you see a negative under a radical, like you just poke the I out. And I was like, okay, if that's how you want to listen to it. Alright. Oh, sorry, announcement. Okay, so now we're going to be solving quadratics using the methods that we've already learned. So remember, we've learned about solving by square rooting, we've learned about factoring, we've done graphing, quadratic formula, and completing the square. So because of our answers today being complex answers with I's, you're not ever going to be able to factor for me with I's, not in this class. You are not going to be able to graph, because graphing in the complex number system looks a lot different. You won't be able to see any of this on your calculator. The only thing you'd be able to have your calculator help you with is if you're determining whether you're going to have real solutions or not. If you have complex solutions, what you're going to have, remember the quadratic formula lesson, you're going to have a quadratic parabola that doesn't cross the x-axis at all. So it's going to look something like this or this, where it's not going to have any x-intercepts. And what that means to me as the math student is my solutions, they exist, they're just going to be complex. Time out. Calling a lot of kids down today. Alright, so here I notice that there's just one variable in the entire problem, and that indicates to me that the method of solving for a quadratic would be the square rooting method. So I'm going to isolate the thing that's being squared, which is this. So I'm going to start by subtracting 10, and I end up with 3x squared equals negative 36, and I'm still not isolated, so one more step to isolate. I'm going to divide by 3. So now I have x squared equals negative 12. We're back. So now we're going to square root both sides. And then just like when we solved an equation through square rooting in the real number system, our answers are both going to be positive and negative, even though there's complex numbers here as well. So x equals plus or minus. Now I want you to use your skill about breaking up a radical. And then the order, remember, was the perfect square, the negative 1, and the leftover. So in 12, the perfect square is a 4, the leftover is a 3, and the negative 1 is a negative 1 in the middle. So when I reduce all those radicals, this becomes a 2, this becomes an I, and then square root of 3 stays. So this is where that kid was being all cutesy and saying like, oh, I'm just going to break down 12 like I always do, and then I'm going to poke the I out, and then stick the I in front of the radical. And I said, all right, fine, if you want to think of it that way, just please don't go off to college telling your professors that you're poking the I out of something. All right, so here's same method. I only see one x in the problem, so we're going to solve by square rooting. Well, this almost looked the same problem for a moment, but it's divided by 2 this time. So 2x squared equals negative 36, and we're going to divide both sides by 2. And this time we get x squared equals negative 18. And then when we square root both sides, we end up with plus or minus. And remember, we're going to break down the radical where it's the perfect square, which is 9, the negative 1 in the middle, and the leftover is a 2. So this becomes 3i, and then square root of 2 left over. Okay. Let's try another one. This is again a perfect square rooting question. We cannot distribute into those parentheses, so please don't, but let's go ahead and multiply by the reciprocal. So let's multiply by a negative 2 on both sides of the equation here. The negative 2 and the 1/2, negative 1/2 will cancel. So you have quantity x plus 1 squared equals negative 10. And then square root both sides here. And this is also the moment where your plus or minus will show up. So we have x plus 1, sorry about the bell, equals plus and minus. Now 10's not going to break down to anything, so you're just going to poke the I out, or reduce it to the square root of negative 1 times the square root of 10. So this becomes I square root of 10. And then finally we're just going to subtract the 1, just like we did in real numbers. So negative 1, and I'm not going to be able to add the I square root of 10 to the negative 1 and simplify it, so I'm going to leave it in this form here.
Hey,
Alright, so that was the method of square rooting, but we could also complete the square to solve, which would end up being a square rooting question. We can do quadratic formula with i's, and we are going to do all of those things, but for now, let's talk about what happens when I want to simplify complex numbers using operations. So operations meaning add, subtract, multiply, and divide. I'm going to pause for a moment because we've got the pledge coming up. Gotta stand, salute the flag and all that. Okay, so the operations that we're going to be doing are, we're going to be adding, subtracting, multiplying, and dividing. So, a complex number is any number in the form a plus bi, where a is the real component, and the bi part is the imaginary component, plus the I. A and b are going to be numbers, and then if you have a complex number where the b is 0, that means you're going to have a number like 3 plus 0i, which would just be 3. So in that case, it would not be an imaginary number, it would be a real number. Okay. So here for number 11, we're going to be adding these two complex numbers together. The idea is you just add the real parts together, and then you're going to add the imaginary parts together. So 4 plus 3 is 7, right? Tricky. Negative 1i plus 2i is positive 1i, which you can just write as plus I, and that is your final answer. All of your answers in this section are going to be written in what we call standard form, which is just a plus bi. So you have to keep working and simplifying until you get to that step. Right, so same thing here. We're going to take our real parts, except this time we are subtracting them. So 7 minus 1 is 6. And then for the i's, I have negative 5i minus a negative 5i. Well, think about that, guys. Negative 5 minus negative 5. These would change to a plus, and we end up with 0i. So you could actually just rewrite this answer to be 6. It's a weird square, sorry. Alright, so here we have this random 6, which is a real number, but you can say it's 6 plus 0i if you want to keep the imaginary part. We're going to subtract this complex number, and we're going to add that complex number. So when I go to pull all the real parts together, I have 6 minus negative 2 plus negative 8. So 6 minus negative 2 plus negative 8, which, yeah, of course you could use a calculator if you wanted to, but the double negatives become a plus. So this is 8 plus negative 8, which is 0. That's fun. And then be careful here, this subtraction is going to go right there as well. So this becomes a minus 9i plus a 4i. So minus 9i plus 4i is a minus 5i. So instead of saying 0 minus 5i, a lot of people will just write this the answer of negative 5i. That would mean the same thing. There's no real part to that complex number. So now we're going to multiply some numbers together and treat I kind of like you would treat an x, so it's kind of like a variable. We're going to distribute the 5i to both terms here in the binomial. So we get negative 10i, and then plus 5i times I would be I squared. Well, this doesn't look like standard form. Remember a plus bi. And I have to go back and remember something about i's. We said at the very beginning of our lesson, I squared was a negative 1. So what that means for us is that this I squared right here, we're going to swap out for a negative 1. So this is really 5 times negative 1 minus 10i. So the only thing I'm going to change here is I'm going to simplify this to say negative 5. And I'm also going to switch the order around because that's the proper order. So negative 5 minus 10i. There's my a plus bi form. So here we have a real number 2 being distributed in. It's going to be a very unexciting question here. Watch this. 22 plus 32i. And that's it, because it is in the form a plus bi. A little more excitement here on number 16. This time we're distributing a 3i. So this becomes 3i times 1 is 3i, and then minus 15i squared. So again, we have to remember that I squared is really a negative 1. So this is 3 times I minus 15 times negative 1. And then I'm going to do a little simplification here. The negative 15 times negative 1 is really positive 15, which I'll write first, and then a positive 3i for the complex, or the imaginary part of the complex number. So these can get kind of interesting when you're simplifying. Those are just monomial distributions of multiplication, but now let's talk about a binomial. So just like with our polynomials, when we distributed a binomial times a binomial, we had to FOIL. So we're going to start with the first times first. 7 times negative 1 is negative 7. And then 7 times 2i is plus 14i. And then negative 4i times negative 1. Oh, my pen's being slow. Hold on. Is a positive 4i. And then at the end here, negative 4i times 2i is negative 8 and an I squared. So that is a far cry from standard form of a plus bi. We have a lot of simplifying to do. I notice that I'm going to be adding these I terms together to get a plus 18i. And then the other thing I have to remember is I squared is going to be changed out for a negative 1. So this part really says negative 8 times negative 1. Well, isn't that just going to be a plus 8 then? So forget that whole term, that's just a plus 8. Now you can take these real parts and say negative 7 plus 8 is 1. There's your solution. Or I shouldn't say solution, there's your simplification to my complex number 1 plus 18i. Alright, same idea here. We're going to be multiplying these together. 6 times 6 is 36. 6 times negative 3i is negative 18i. And then this is kind of interesting. We end up with a positive 18i. We'll talk about what this means in a minute. And then 3i times negative 3i is negative 9i squared. So once again, I'm going to collect my like terms in the middle here, but this is great because they just cancel each other out. And then the I squared, remember, we're going to change that out for a negative 1. So what you have here is you have a negative 9 times a negative 1. So that term is really just a plus 9. And over here you still have a 36, and then you have nothing in the middle here. So when I go to add my real parts together and combine them, I get 45. You could say 45 plus 0i, but it's just 45. So new vocab word for you, and we actually have talked about this. This is the good twin, evil twin pattern we talked about before. This is called a conjugate pair. And if you notice that you're multiplying conjugate pairs together, it's wonderful because the middle parts of that foiling question will cancel out. Now, a lot of kids see this question and they think they're just supposed to square the 3 and the 4. That's not how this works. Remember, it's a 3 plus 4i times another 3 plus 4i. So it's more complicated than just squaring the numbers. So we're going to start with 3 times 3, which is 9. And then 3 times 4i plus another 3 times 4i is 12i plus another 12i. I don't like to skip steps on these because they can get really gross. 4i times another 4i would be positive 16i squared. So we will be collecting these 12s together. They're not going to cancel. It's going to give you a positive 24i. And then I'm going to remember that I squared is really a negative 1. Oops. So this entire term right here is 16 times negative 1. This is just a negative 16. So when I go to add my real parts together, 9 plus negative 16, or 9 minus 16, is negative 7. Lovely. And now for the big one, the division. When you divide a complex number by another complex number, I know it doesn't look like it's a bad idea to just leave it like that, but it goes against that weird rule in math that says you can't have a radical in the denominator, because remember I was the square root of negative 1. So this is really like 2 times the square root of negative 1, and we're not allowed to have that. So what we're going to do is we're going to use our trick with the complex conjugates that we just learned about. Look at the denominator, and I want you to come up with what his complex conjugate would be. And whatever that is, we're going to multiply it to both the numerator and the denominator to keep my fraction balanced. So the complex conjugate would be the same factor, but the last term of the factor has to have the opposite sign. So instead of 1 minus 2i, we're going to use 1 plus 2i. So the bi part is the sign that you're changing. So up here, we're also multiplying by 1 plus 2i, and we're about to have a lot of fun with multiplication. You ready? We're going to multiply this numerator out. It's going to be lovely. We're going to multiply this denominator out. It's going to be even lovelier. And then we'll see what the simplified answer reduces to. All right, hang with me, guys. So this numerator, do not skip steps. It's not worth it. 5 times 1 is 5. And then outside and inside multiplied together would be, let's see, plus 10i plus 3i. And then my last numbers multiplied together are a plus 6i squared. Leave it alone for a minute. We'll come back to that. All right, we're going to do the same thing here in the denominator. 1 times 1 is 1. And then plus 2i minus 2i. Don't skip steps. I'm telling you, it's not worth it. And then negative 2i times 2i is negative 4i squared. So what we need to do now is simplify this numerator as much as we can and simplify this denominator as much as we can, and then we'll see what we're working with. So remember, we're going to add these i's together, so these are going to become 13i. But we also have to remember that I squared is really a negative 1. So 6 times negative 1, this term is really a negative 6. So now we're going to combine this 5 and this negative 6 together. And we're going to get negative 1 for the real part, plus, this is 13i. So there's my real numerator once I simplified. Now my denominator is a different story. I have a 1. The plus I and minus, the plus 2i and the minus 2i are going to cancel out, so they're gone. And then remember, I squared is negative 1. So this is negative 4 times negative 1. This is just a positive 4. So remember, last time we multiplied conjugates together, they just ended up giving me a real number. Like in that example, it was 45. Well, this time it's 1 plus 4, which is 5. And then remember, I want my answer in the form a plus bi. So what we're going to do now is we're going to take this 5 and we're going to divide it underneath each piece of this numerator. So I get negative 1/5 plus 13/5 I. And now we are in a plus bi form. I know, it's a lot of work. The division ones are clearly the most difficult ones, so hang with me. All right, let's talk about what the conjugate would be for this one. 1 plus I, the conjugate would be 1 minus I. And we're going to go ahead and put parentheses around everybody. Let's do this. All right, big fraction bar. So 2 times 1 is 2. And then 2 times Where are we at? Negative I is negative 2I. Negative 7 times 1 is negative 7I times 1 is negative 7I. And then negative 7I times negative 1I is positive 7I squared. All right, multiplying 1 times 1 is 1. Remember, those conjugate middle terms are going to cancel out, so don't be surprised when they do. And they will. And then my final term there, negative I times positive I is negative I squared. So, again, we're going to simplify this numerator as best we can, and then simplify the denominator. It's going to be lovely. All right, numerator. Remember, this I squared is a negative 1, so 7 times negative 1, this term's just going to be a minus 7. We're going to combine these i's together, and we should also go ahead and just add the 2 and the negative 7 together while we're at it. So 2 plus negative 7 is a negative 5 for the real part. Negative 2i minus 7i is negative 9i. And then the i's down here will cancel, but remember what I squared is, it's negative 1. So if I'm subtracting a negative 1, aren't I just adding 1? So now when I add 1 plus 1, I get dos. And then final answer in a plus bi form, negative 5 halves minus 9 halves I. Blech. And I got that by just dividing each part of the numerator by the 2 separately. So, those are i's for you. Oh, one more. We have this time a little bit of a different denominator. Instead of a binomial denominator, you have a monomial. When this happens, all you need to do is multiply by an I. So keep that in mind. And then up in the numerator, you will have to distribute that I. But in the denominator, it's less work, so that's exciting. All right, so this numerator, if I distribute the I get negative 2I plus 5, and then I times I will be I squared. Over 3I times I, which is 3I squared. And then there's not a lot of simplification other than, remember what I squareds are? They're really negative 1s. So this is 5 times negative 1, so this term right here is negative 5. I'm going to write that first. I still have a minus 2i. And then our denominator is 3 times negative 1, which is negative 3. So using my little trick of writing it in a plus bi form, you have to be a little bit careful here though, guys, because negative over negative will reduce to a positive 5/3, and then negative over negative again will reduce to a positive 2/3 I. So clearly, if you have a monomial denominator, it's like way less work, so that's exciting. All right, this next question here is taking what is really a very complicated concept, and I'm just breaking it down to the bare bones for you. So if we're looking at an electrical circuit, this is where complex numbers are applied a lot during electrical engineering and electricity in general. So the overall resistance is known as impedance, and they use Z typically for the variable to indicate impedance. And that could be found by adding all of the components together. So when you're in a circuit, you have capacitors and resistors that are rerouting the currents. So it's kind of out of my expertise area, but those of you who are looking at engineering, you'll probably take a whole bunch of courses in electricity, so have fun. So there's the formula we're going to be using. A resistor is a real number value, and and the inductor. I forgot about the inductor. The inductor is a pure imaginary number, and they're going to refer to it as Li because it's imaginary. So L will be a number, a coefficient, I will be the number I. And then a capacitor is going to have a negative coefficient with an I next to it. So if our resistor is 6 ohms, that's what that label means, and the inductor is 10 ohms, and the capacitor is 5 ohms, and I go into this formula here, I'm going to be able to figure out the total impedance. So the resistor, I'm just going to put a 6 in place of R, plus the inductor is 10, but with an imaginary component, and then we're going to subtract the capacitor, which is 5, with an imaginary component. So all you need to do for me is simplify your i's. So this becomes 6 plus 5i, and then you can go ahead and I think we can label it with ohms. Again, not my area of expertise, so I'm not an electrical engineer. So part B here is very similar, a resistor of 13 ohms plus, now this time you have 2 different inductors, so you're going to be adding 4 and 5 i's. So if you want to write them separately, you can, or if you want to just change that to 9i, that's fine as well. And then remember, capacitors, we're going to be subtracting that imaginary component. So this is 9i minus 7i, so we end up with 2i for the imaginary component, so 13 plus 2i. That's the overall impedance for your circuit. That's clever. Alright, so really small print says, good news. Now we get to go back and do all of our quadratic solving methods except for factoring and graphing with imaginary solutions. Yay!